So finding extrema on surfaces using partial derivatives. What's the key idea here? The key idea is that assuming that your surface is differentiable, right? Assuming your partial derivatives exist, um, then if you have a max, right, or a min, then what would the tangent plane look like at that point? It's gotta be horizontal, right? If you're at the very top of a mountain, the very peak of a mountain, or the very bottom of a valley, right? It's gonna look like a the tangent plane is gonna look horizontal, right? So that's the key insight here, right? So to search for now, how do you determine a horizontal tangent plane? Well, what gives us the direction vectors of the tangent plane? The partial derivatives do, right? So what would you need? You would need df the dx equals 0 and df dy equals 0, right? At those critical points, right? So these are so just like in Calc 1, right? Where the partials are 0, you typically call them critical points, right? Um, right, so such points are typically called critical points. Now, but also just like in Calc 1, the partials being 0 is not sufficient to determine to conclude there's definitely a max or a min there, because you can have saddle points, just like in Calc 1, right? So it is possible, right, to have the partial derivatives both be 0, right, but not have a max or min, right? And such points are called saddles, right? Right, because we would have been happy if we had a max or min, right? So the max and mins collectively are called hapules, otherwise saddle. So okay, so let's then go on to our algorithm for determining these, right? So how can we tell? So, right, how can we tell without, just drawing the graph and plotting lots of points or appealing to a computer algebra system or something like that? How can we tell a max versus min from a saddle? Right. Well, it turns out what you have to do is you have to look at second derivatives, right? Look at second derivatives. And this is much like in Calc 1, right? You have the second derivative test, which helps you, where you look at concavity, right, to tell max from min from saddle. Hopefully, right? The same thing here. This is the idea. And so let's look at an example of, or sorry, let me state the second derivative test, right? So this is the multivariable, right? Second derivative test. I'm not going to prove it here. It's a quite a bit of work to prove. It essentially boils down to just completing the square in two variables and then seeing if the resulting surface looks like an upward facing parabola or downward facing parabola or a mix of both. So it's basically just completing the square, but you're completing the square over two variables, and it's kind of a mess algebraically. But so here I'm not going to show that here, but I'm going to show kind of how it works, right? So just how to apply it. So what do you do for the multiple variable second derivative test, right? So say we're given a surface, right, f of x, y, and um, we'll say that um, let's say the first and second derivatives, right? All the first and second partials are well-defined, continuous, all that jazz, right? Um, then if AB is a critical point, right? Meaning what? Meaning that the first partials at AB are both 0, right? So you already found a critical point. And now you want to classify it further, right? Then we're going to define the discriminant. And what the discriminant is it's the product of the second partials with respect to x and y minus the square of the mixed second partial, right? So this is the discriminant, how we define it. And these subscripts indicate partial derivative, right? So just notation wise, if you haven't seen that notation before, that's perfectly fine. This is just a shorter way to write this, right? And similarly for FYY is just a shorter way to write this, right? And then this is just a shorter way to write this. DDY of DDX of F, right? So you can see why the subscript notation is nice, because it just gets cumbersome using the differential notation here. So that's what those subscripts indicate. The subscript notation for partials is very common, especially if you're using higher partials, second or third or whatever, because it just gets annoying to write the other way. Okay, so you define that discriminant, and then here's what we say from there. So once you have your discriminant defined, from there, say if the discriminant, it turns out, if the discriminant is positive, then you can use the old Calc 1 second derivative test. Right? So you can just say then, and what was the Calc 1 second derivative test? If the second derivative with respect to x, like you would do back in Calc 1, right? If that is positive, then, right, what was that case? Second derivative positive means min, implies min, right? Second derivative negative implies max, right? So this is where the old Calc 1 second derivative test lives as a subcase of this multivariable second derivative test. So when the discriminant is positive, then you get to just go do the old Calc 1 thing. Right? If the discriminant is negative, then we have a saddle. Right, so this is min versus max versus saddle. And then if the discriminant is 0, then this test gives no info. So you have to go on and do something else, right? Maybe take a secondary power series approximation of your function at that point, or third degree or fourth degree, or right. You have to do something else. Basically you can have, if the discriminant is 0, you could have a min or max or saddle at that point. Okay, so this is our second multivariable second derivative test, right? Which is kind of a bit of a mouthful to say, right? It starts up here and goes all the way down. Yeah, right. This whole thing is our multivariable second derivative test. Okay, so I want to do this for I want to run this algorithm for a surface just to show it demonstrated. And in particular, I want to do a surface that we were just working with in a previous video, right? So let's find and classify. So find meaning find your critical points, right? Classify meaning apply second derivatives, right? All critical points for this surface. So f of xy equals root 1 minus 4 x squared minus y squared. Now this is a surface that we drew the graph of in previous 2 videos actually, right? And right, what did it look like? It looked like this little half ellipsoid, right? So you can kind of see, if you have a really good sense of the graph, you can kind of see what's going on. Basically here, we're just going to have a, it's not cross. But here we're just going to have, we should just have a max at the origin and nothing else, right? Based on having a good sense of the graph, right? So I'm hoping this comes out as max at 0, 0, right? So let's do this. So first, let's find the critical points. And what do the critical points look like here? I have df dx equals, this is negative 4x over root 1 minus 4x squared minus y squared, right? And I have df dy, right, was negative y over root 1 minus 4 x squared minus y squared. And these I'm taking just from up above. In the previous video, we calculated these partial derivatives up here, right? So we had already done those calculations. But again, previous video in the Calc 3 playlist here, we did those calculations. So I'm just copying down those formulas. But now I want to set each of those equal to 0, and I want to solve that as a simultaneous system of equations to find my critical points. Well, here I just get a fraction is 0 if and only if the numerator is 0. Again, a fraction is 0 if and only if the numerator is 0. So here, the algebra works out pretty easy. It just says x and y equals 0, right? Now, if you have messier formulas, there might be more to do there. You might have to factor or find roots of some polynomial, whatever. Here we only get one critical point, 0, 0. So that's good. That agrees with this graph. Let's now look at classifying it, right? So let's now classify via the second derivative test. Right? Okay, so this is going to be a little bit ugly because I have to take the second partials here, right? So let's see what happens. So I have fxx, right? I need to calculate these second partials. So fxx it's the partial of the partial, is what that notation means, right? But we already did the first partial, so I can use that here in my calculation. And now, sadly, I really need a closure rule, right? Because I have an x in the top and the bottom. So let's take our Ricola and do our best yodel voice. What happens here? I have my right, my low d high, right, minus high d low. There you go, right? All over low squared. Right, there's my second partial. And now this is the second partial in general at xx, right? Fortunately, I don't need it at a general xx, right? I need it at 0, 0, right? So it looks like this is a hideous mess. And if you start trying to clean this up, it's gonna be a hideous mess. But I'm only interested in the value of it at my critical point. So I would say just right away, don't even try to clean this formula up algebraically. Just right away, plug in 0, 0, and it gets way simpler, right? Because this whole term here, the really ugly term, that whole term is going to vanish, right? And you just get, what do we get? We just get negative 4 over 1. Just get negative 4. That's it. There we go. Right. So it looks like really horrible, but then when you plug in the critical point, it's not that bad. Okay. let's also do fyy, right? Which is, again, it's going to be the partial of something we already have. It's the y partial of the y partial. And we had this y partial already, right? This was our y partial. And this, again, I need a quotient rule, right? So I do low d high minus high d low. Right, all over low squared. And which again looks really bad until you actually plug in the values that we're interested in. And here we just get -1. Okay, not so bad. There we go. So there's fxx, fyy. Then I have the mixed partial, fxy. And here it's actually not entirely obvious, but you can do it either way. You can it's called Clairaut's theorem. It's a very cool theorem. You can it doesn't matter which order you take the partial derivative in. Um, you can find very obscure. There are some preconditions there. You can find very obscure surfaces for which it does matter what order. But if you have basically continuous derivatives and second derivatives, then you could always trade the, and I think third maybe. I'd have to check the preconditions there. But if you certainly if you have all continuous derivatives of all order, then it doesn't matter if you take the x then y or y then x, right? For a mixed partial. So you can do whichever one you want. Here, sometimes one is actually a lot cleaner than the other. So look if it matters, right? Here it doesn't matter. They're about equal in this particular case in terms of mess. So I'll do the y partial in terms of x. So this one, if you notice, is actually a little cleaner because we don't need chain rule here. Sorry, we don't need quotient rule here because we're treating y as a constant and the numerator is minus y, right? So there's no x in the numerator. So this is actually a little cleaner, right? So I can do this as what? I'm doing this just as power rule and chain rule, right? So it's negative y. I have my my constant here. It's going to kick out for my power rule, right? And -1/2 as a constant. The exponent goes down by 1, so it's going to go down to -3/2, right? And then I'm going to multiply by the derivative of the inner, which is going to be -8x. Okay, so then once again, plug in 0, 0, right? At 0, 0 is just 0, right? Because the numerator is 0 and the denominator is not 0. Okay. So now I could put these three quantities together to get my discriminant, right? So the discriminant, which is fxx times fyy minus fxy squared, FYI, it's fxx fyy minus fxy squared, FYI. Sorry. The let's then put these three quantities together. What do we get? I get -4 times -1 minus 0 squared is 4. It's positive 4, right? And this makes me happy because it means in this case my discriminant is positive. So I can do my old Calc 1 second derivative test, right? So positive discriminant means go back to Calc 1, right? And we do what? We say then the second derivative with respect to x was negative, right? Because that was the -4, right? This is negative. So the second derivative with respect to x was negative. So negative second derivative back in Calc 1 means what? It means a max, right? So we have a max, just like the graph predicted way back up here. That little red dot, max at 0, 0. That's what we were hoping for, right? So it confirmed our suspicion from the graph. right, was confirmed by this applying this second derivative test. All right, thanks.